Welcome to this problem walkthrough. Today, we'll be exploring LeetCode number 1701, titled Average Waiting Time. This is a fascinating problem that challenges us to optimize the computation of average waiting times for customers in a restaurant. Let's dive into the problem, discuss the various approaches, and break it down step by step. In this problem, we are tasked with calculating the average waiting time for a series of customers. Each customer is represented by a pair of integers in a 2D array called customers. The first value in each pair is the arrival time of the customer, and the second value is the time required to prepare their order. When a customer arrives, they must wait for all previous customers' orders to be completed before their order can begin. The waiting time for a customer is defined as the difference between the time their order is completed and their arrival time. Our goal is to compute the average of these waiting times across all customers and return the result as a floating point number, rounded to 5 decimal places. The problem also specifies the input and output formats. The input is a 2D array, where each subarray represents a customer's arrival time and preparation time. The output is a single floating point number representing the average waiting time. Now let's look at the first example. Here, the input is a list of customers, 1, 2, 2, 5, 4, 3. For the first customer, who arrives at time 1, their order takes 2 units of time to prepare. This means their order is completed at time 3, and their waiting time is 3 1 equals 2. The second customer arrives at time 2. Since the first customer's order is completed at time 3, the second customer's order starts at time 3. Their order takes 5 units of time to prepare, so it completes at time 8. The waiting time for the second customer is 8 2 equals 6. The third customer arrives at time 4. At this point, the second customer's order is still being prepared and will complete at time 8. Thus, the third customer's order begins at time 8 and requires 3 units of time to prepare. The third customer's order is completed at time 11, resulting in a waiting time of 11 4 equals 7. Adding up the waiting times for all 3 customers, we get 2 plus 6 plus 7 equals 15. To find the average waiting time, we divide the total waiting time by the number of customers. 15/3 equals 5.00000. This is the output for the first example. Let's now consider the second example, where the input is 5, 2, 5, 4, 10, 3. The first customer arrives at time 5, and their order takes 2 units of time to prepare. Their order is completed at time 7, giving them a waiting time of 7 5 equals 2. The second customer also arrives at time 5. Since the first customer's order completes at time 7, the second customer's order starts at time 7. Their order takes 4 units of time, so it completes at time 11, leading to a waiting time of 11 5 equals 6. For the third customer, who arrives at time 10, the second customer's order is completed at time 11. The third customer's order begins at time 11 and requires 3 units of time to prepare, completing at time 14. This results in a waiting time of 14 10 equals 4. Adding up the waiting times for all 3 customers, we get 2 plus 6 plus 4 equals 12. Dividing this by the number of customers gives the average waiting time, 12/3 equals 3.66667. Finally, the problem specifies some constraints and edge cases to consider. For example, if there is only one customer, their waiting time is simply the preparation time for their order. If there are large gaps between arrival times, the waiting time for later customers might be minimal. Similarly, if all customers arrive at the same time, the waiting time depends entirely on the order of preparation. The algorithm must also handle large inputs efficiently to avoid exceeding time limits. To begin, we considered the brute force approach, which directly simulates the problem as described. In this method, we process each customer one at a time, calculating their waiting time by iterating through all prior customers to determine when the current customer's service can start and end. After calculating the waiting time for each customer in this way, we sum these values and compute the average. While this approach mirrors the intuition behind the problem, it's computationally expensive. For every customer, we perform nested iterations to account for the cumulative service times of all previous customers. This results in a time complexity of O(n²), where n is the number of customers. As n grows, especially for larger input sizes like 100,000 customers, this inefficiency becomes a significant bottleneck. Therefore, while conceptually straightforward, this approach is impractical for large datasets due to its quadratic time complexity. Now, to address the inefficiencies of the brute force approach, we developed an optimized strategy that processes the customers in a single pass while maintaining a running total of the service time. Here's how it works. We initialize two variables, current_time, which tracks the moment when the next customer's service can begin, and total_waiting_time, which accumulates all the waiting times. As we iterate through the customers, if a customer arrives after the current service time, we adjust current_time to their arrival time. We then add their service time to current_time and calculate their waiting time as the difference between current_time and their arrival. This waiting time is added to total_waiting_time. At the end of the iteration, dividing total_waiting_time by the number of customers gives the average waiting time. This method avoids redundant computations by leveraging the cumulative service time, allowing us to calculate each customer's waiting time in constant time. With a time complexity of O(n) and a space complexity of O(1), this approach is far more efficient and scalable. Key insights helped us refine our strategy. First, the sequential dependency between customers means that each customer's service can only begin after the previous one is completed. This dependency can be efficiently tracked with a single variable, current_time. Second, by maintaining a running total of the cumulative service time, we eliminate the need for redundant iterations, significantly improving efficiency. Finally, the greedy nature of the problem ensures that the optimal solution is achieved by processing customers in the order of their arrival, as no alternative strategies, like divide and conquer, would apply here. Considering these observations, the optimized approach is the clear choice. It is efficient, with an O(n) time complexity, and straightforward to implement, requiring only minimal bookkeeping. While the brute force method provides an intuitive understanding of the problem, the optimized approach achieves the same result with far superior performance, making it ideal for competitive programming and large-scale inputs. When comparing the brute force and optimized approaches, the trade-offs become clear. The brute force method prioritizes simplicity, directly simulating the problem, but at the cost of poor performance due to its O(n)² time complexity. This makes it unsuitable for larger inputs. In contrast, the optimized approach strikes the right balance between efficiency and clarity, leveraging a linear time complexity that ensures scalability while maintaining simplicity in implementation. The greedy nature of the problem further reinforces the chosen strategy, as sequential processing is both necessary and sufficient. Alternative methods, such as divide and conquer, are not applicable due to the inherent dependency on processing customers in arrival order. In summary, the optimized approach is the most practical and efficient solution, taking full advantage of the sequential and greedy characteristics of the task to deliver the best performance. To tackle the problem of calculating the average waiting time for customers, we start by analyzing the essentials. Each customer is represented by their arrival time and the duration needed to process their order. The task is to compute the average waiting time, which includes both the time they waited for the system to become available and the time their order took to process. To achieve this, the input is a list of customers, where each customer is a pair of arrival time and processing time. The output is the calculated average waiting time for all customers. A simple brute force approach can be used initially to simulate the process. Here, we iterate over each customer, keeping track of when the system becomes free and adding the calculated waiting times. If a customer arrives when the system is idle, the system waits for them. Otherwise, the customer waits for the system to finish processing prior orders. We then accumulate the total waiting time and divide it by the number of customers to compute the average. The brute force approach continues by adding each customer's waiting time to the total waiting time. Once all customers are processed, the average waiting time is calculated by dividing the total waiting time by the number of customers. Now, let's consider the computational complexity of this approach. The time complexity is O(n), as we process each customer exactly once in a single loop. This makes it efficient for a sequential processing system. The space complexity is O(1), as no additional data structures are required beyond the variables for tracking current time and total waiting time. This simplicity ensures the approach is both time efficient and memory efficient. Now, there are several key insights that make this algorithm effective. First, customers are processed in the order they arrive, so no sorting is needed, enabling a straightforward linear scan. Second, the system handles idle times naturally by updating the current time to the next arrival time if no customers are waiting. Third, waiting time is calculated as the difference between the system's current availability and the customer's arrival time. If the system is idle, waiting time for that customer is 0. Additionally, edge cases are important to consider. For instance, if there is only one customer, their waiting time is always 0. If all customers arrive at the same time, waiting time accumulates based on the processing order. In cases where there are large gaps between arrivals, the system simply adjusts to the next arrival time, avoiding unnecessary delays. The algorithm relies on minimal data structures, making it highly efficient. The input list holds customer data as pairs of arrival and processing times, allowing for straightforward iteration. Beyond that, only a few variables are needed. The current_time variable keeps track of when the system is available for processing the next customer, and total_waiting_time accumulates the waiting times. These two variables are sufficient for managing the process and calculating the final result, meaning no additional storage or complex data structures are required. To better understand the algorithm, let's walk through an example. Consider 3 customers with the following data. The first customer arrives at time 1 and has a processing time of 2, the second arrives at time 2 and requires 3 units of processing, and the third arrives at time 3 with a processing time of 1. For the first customer, the system is idle until their arrival at time 1. The system then processes their order, completing it at time 3. Their waiting time is 0, which is added to the total waiting time. For the second customer, they arrive at time 2 while the system is still busy processing the first customer. They wait for 1 unit of time, as the system becomes available at time 3. The system completes their processing at time 6, and their waiting time of 1 is added to the total. Finally, the third customer arrives at time 3 but must wait until the system finishes processing the second customer. Their waiting time is 3, and the system completes their processing at time 7. The third customer's waiting time of 3 is added to the total waiting time. Summing up, the total waiting time for all 3 customers is 0 plus 1 plus 3, which equals 4. To calculate the average waiting time, we divide this total by the number of customers, which is 3. This gives an average waiting time of 4 divided by 3, or approximately 1.33. Therefore, the final output of the algorithm is an average waiting time of 1.33. This example demonstrates how the algorithm efficiently handles the sequential processing of customers while accounting for idle times and waiting periods, producing an accurate and reliable result. This code solves LeetCode problem number 1701, average waiting time. The function average waiting time calculates the average waiting time for a list of customers, where each customer is represented as a pair of arrival time and processing time. We start by initializing the total_waiting_time to 0 and current_time to keep track of the system's time. These variables will accumulate the total waiting time and manage the system clock, respectively. The function processes customers sequentially using a loop. For each customer, we first check if the system's current_time is less than the customer's arrival time. If so, the system waits until the customer arrives by setting current_time to the customer's arrival time. Once the customer is being served, we add their processing time to the current_time and calculate their waiting time as the difference between current_time and their arrival time. The waiting time for each customer is added to the total_waiting_time. After processing all customers, the average waiting time is calculated by dividing the total_waiting_time by the number of customers. This approach efficiently computes the result in O(n) time complexity, as each customer is processed exactly once. Edge cases, such as customers arriving at different times or overlapping processing times, are handled naturally by the sequential processing logic. Finally, the function returns the calculated average waiting time as a floating point value. This is the Java implementation of LeetCode problem number 1701, average waiting time. The logic is identical to the Python solution, iterating through each customer to calculate their waiting time and updating the total waiting time. Key differences include type declarations for variables, adherence to Java's array handling, and the use of long for large values to avoid overflow. The function returns the average waiting time as a double. In this problem, we are tasked with calculating the average waiting time for customers in a restaurant. Each customer is represented as a pair, arrival_time, processing_time, where the arrival time indicates when the customer shows up, and the processing time is the duration it takes to serve them. The waiting time for a customer is the difference between the time they finish being served and their arrival time. If no customers are present yet and the chef is idle, the chef waits until the next customer arrives. The objective is to compute the average waiting time for all customers. Let's look at an example with the input customers equals 1, 2, 2, 5, 4, 3. First, we initialize total_waiting_time to 0 and current_time to 0 as well. For the first customer, arrival equals 1, processing equals 2, the current time is less than their arrival time, so we update current_time to 1. The chef serves the customer, so the current time becomes 3 after adding the processing time. The waiting time for this customer is 3 1 equals 2, and we add it to the total, making total_waiting_time equals 2. Now, for the second customer, arrival equals 2, processing equals 5, the current time is already greater than or equal to their arrival time, so the chef can immediately begin serving them without waiting. The current time is updated to 8 after adding the processing time. The waiting time for this customer is 8 2 equals 6, which we add to the total, bringing total_waiting_time to 8. For the third customer, arrival equals 4, processing equals 3, the current time is again greater than or equal to their arrival time, so no idle time is needed. The current time becomes 11 after processing, and the waiting time is 11, 4 equals 7. Adding this to the total gives total_waiting_time equals 15. Finally, we calculate the average waiting time by dividing the total waiting time by the number of customers. With 3 customers, the average is 15/3 equals 5.0, which is the output. In another example, customers equals 5, 2, 5, 4, 6, 3, we start with total_waiting_time equals 0 and current_time equals 0. For the first customer, arrival equals 5, processing equals 2, the current time is less than their arrival time, so we update current_time to 5. After serving them, the current time becomes 7, and their waiting time is 7 5 equals 2. Adding this to the total gives total_waiting_time equals 2. For the second customer, arrival equals 5, processing equals 4, the current time is already greater than or equal to their arrival time, so the chef continues immediately. The current time becomes 11, and their waiting time is 11 5 equals 6, which we add to the total, making total_waiting_time equals 8. For the third customer, arrival equals 6, processing equals 3, the chef starts immediately since the current time is greater than their arrival time. After processing, the current time becomes 14, and their waiting time is 14 6 equals 8. The total waiting time now is 16. Dividing the total by the number of customers gives an average of 16/3 equals 5.33, which is the output. In the final example, customers equals 2, 3, 6, 1, 7, 3, we begin with total_waiting_time equals 0 and current_time equals 0. For the first customer, arrival equals 2, processing equals 3, the current time is less than their arrival time, so we update current_time to 2. The chef serves them, and the current time becomes 5. Their waiting time is 5 2 equals 3, which we add to the total, making total_waiting_time equals 3. For the second customer, arrival equals 6, processing equals 1, the current time is less than their arrival time, so we update current_time to 6. After serving, the current time becomes 7, and their waiting time is 7 6 equals 1. Adding this to the total gives total_waiting_time equals 4. For the third customer, arrival equals 7, processing equals 3, the current time is already equal to their arrival time, so the chef begins immediately. The current time becomes 10, and their waiting time is 10 7 equals 3. Adding this gives total_waiting_time equals 7. Finally, dividing the total by the number of customers gives an average of 7/3 equals 2.33, which is the output. The time complexity of this solution is O(n), where n represents the number of customers in the input list. This efficiency comes from the fact that the algorithm processes each customer exactly once. It uses a single for loop to iterate through the list, and during each iteration, it performs several constant time operations. These include checking and updating the current time relative to the customer's arrival, adding the processing time to the current time, and calculating and adding the waiting time to the total. Each of these operations takes O(1) time. After processing all customers, the algorithm computes the average waiting time by dividing the total waiting time by the number of customers, which is another O(1) operation. Since the total work scales linearly with the number of customers, the overall time complexity is O(n). The space complexity of this solution is O(1), meaning it uses a constant amount of additional memory regardless of the input size. This is because the algorithm only requires a few variables, such as total_waiting_time and current_time, to keep track of the calculations. These variables take up constant space. Additionally, the algorithm processes the input list in place, without creating any additional data structures like lists or dictionaries. It simply reads the values from the input list without modifying them. As no extra space is allocated based on the size of the input, the space complexity remains O(1). The solution maintains its efficiency across all scenarios. In the best case, all customers arrive sequentially without any gaps in their arrival times. Here, the algorithm still processes each customer once, giving it a time complexity of O(n). In the average case, where arrival and processing times are random, the time complexity remains O(n), as each customer is processed in constant time. Even in the worst case, where there are large gaps between customer arrivals, the algorithm only updates the current time and processes each customer individually, so the time complexity is still O(n). Comparing this to a brute force approach, which might simulate each customer's waiting time by iterating through previous customers, we see a significant improvement. A naive solution could result in a time complexity of O(n², in the worst case due to redundant calculations. The optimized approach avoids this by maintaining a running current_time and directly calculating waiting times, reducing the time complexity to O(n). To mathematically prove the big O complexity, let n represent the number of customers. Each iteration of the loop performs a constant amount of operations, which is O(1). After n iterations, the total work becomes approximately n multiplied by O(1), resulting in O(n). Since the algorithm does not use nested loops, recursive calls, or additional data structures, no higher-order terms like O(n²) are introduced. Regarding space, the algorithm does not allocate memory based on the input size, as it only uses a constant number of variables. This ensures the space complexity remains O(1). Therefore, the solution is time optimal with O(n), and space efficient with O(1). In problem solving, there are a few common mistakes that can trip you up if you're not careful. First, failing to optimize for edge cases is a frequent issue. Edge cases include things like empty inputs, single-element arrays, or very large datasets. These scenarios often reveal hidden bugs, such as index out-of-bounds errors when handling arrays of size 0 or 1. Testing these explicitly is critical to ensure your solution is robust. Next, making incorrect assumptions about input order can also lead to errors. For example, if you assume the input is already sorted but it's not, your algorithm might fail. Always verify constraints or explicitly sort the data when necessary. Finally, overlooking time complexity in nested loops can result in inefficient solutions. Using brute force, like iterating through all pairs in the input, might work for small datasets, but it becomes impractical for larger ones. Instead, look for ways to optimize to O(n) log n, or even O(n) complexity wherever possible. Another mistake to watch for is mismanaging data structures. Choosing the wrong data structure can introduce inefficiencies. For instance, using an array for frequency counts might result in O(n² scans, whereas a hash map or dictionary can reduce this to O(n) with O(1) lookups. Selecting the right data structure can make your solution both simpler and faster. Additionally, space complexity is often overlooked. While optimizing for time, it's easy to forget the memory overhead of your approach. For example, creating unnecessary auxiliary arrays for intermediate results can waste memory, especially for large inputs. Instead, in-place modifications or more memory-efficient techniques should be considered. Balancing time and space is key to crafting an efficient solution. When approaching problems, there are several strategies that can set you up for success. Recognizing common patterns, such as sliding window, two-pointer techniques, or dynamic programming, is crucial. Many problems follow these patterns, and identifying them early can significantly speed up your process. It's also important to clarify requirements with the interviewer or problem description. Ask about edge cases, constraints, and input sizes to avoid unnecessary assumptions and ensure your solution aligns with expectations. A good habit is to iterate through solutions, start with a brute force approach to validate correctness, and then refine and optimize step by step. As you do this, clearly communicate your thought process to demonstrate how your solution evolves. Finally, understand the trade-offs between time and space. For example, a solution with O(n) time but O(n) space might be acceptable, but if memory is limited, you may need to explore alternatives that use less space, even if they take longer to run. Some related problems can help you practice and reinforce these techniques. For instance, TwoSum on LeetCode uses hash maps to optimize performance over a brute force approach. The longest substring without repeating characters problem demonstrates the power of the sliding window technique for substring-related problems. Another classic is 3-sum, where sorting and two-pointer strategies are essential for improving efficiency. Finally, the container with most water problem is another excellent example of the two-pointer approach, reducing time complexity from O(n)² to O(n). Studying and solving these problems can help you recognize patterns and refine your ability to apply the right techniques effectively. When solving problems, it's also important to evaluate alternative approaches and their trade-offs. Brute force is a straightforward method that guarantees correctness, but it's often inefficient, with time complexities like O(n)² or worse. It's best used for small inputs or as a starting point to refine your solution. The two-pointer technique is particularly effective for problems involving sorted inputs or pair-finding tasks, reducing time complexity to O(n) or O(n log n). Sliding window techniques are ideal for subarray or substring problems, offering linear time complexity, though you need to carefully handle boundary conditions. Hash maps or dictionaries are great for lookups and frequency counts, achieving O(n) time complexity, though you should be mindful of the increased space usage. Lastly, dynamic programming is a powerful approach for problems with overlapping subproblems, like finding the longest common subsequence. It balances time and space efficiency but requires careful management of states to avoid unnecessary computations. Great job making it to the end. To summarize, we tackled the average waiting time problem, discussed its brute force approach, and highlighted key takeaways. Remember, problems like these are great for honing simulation and optimization skills. Thanks for watching, and we'll see you in the next walkthrough. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!